Greetings, curious minds. What do all of these things have in common? If you guessed 433 MHz radio frequency communication, then you guessed right. And this is what this video is all about. In particular, it's about these cheap and easy to interface with transmitter-receiver devices. As you can see, they are also easily available and quite cheap from international websites such as this one or from your local electronics shop. This is where I got them, from a local shop. You can also get them from a variety of places. Before we start using them, we'll do a quick refresher about radio frequency modulation techniques, because our device is using one of these techniques, in particular ASK modulation, which stands for amplitude shift keying. We'll see about that. After we branch over the theory, we'll have some fun experimenting, both with an Arduino and with an oscilloscope, to see how these devices transmit and receive, at least on the digital side. Because on the analog side, we're dealing with hundreds of megahertz frequency, which neither my oscilloscope nor the Arduino can handle. Also, in this video, we'll talk about what you can use these devices for. For example, you can use them to communicate between your own electronic devices. Say you're trying to build your own toy car, such as the one in this video, such as the commercial version. And you could use a couple of Arduinos and one of these transmitter-receiver device pairs to control your toy car. You can also use these devices for more practical purposes, such as interfacing with existing commercial products such as remote keys, remote doorbells, spear sensors, and other smart appliances, which happen to operate on this frequency. Not all of them do, and not all of them have this encoding, but there's quite a few of them out there which do operate on this frequency and use ASK encoding. Before we go on, there's one more thing I'd like to mention here. There are other radio communication technologies such as Wi-Fi, Bluetooth, Zigbee. Yes, they're all radio beneath the surface. It's just the protocols they define over the radio which makes them, let's say, special. I'm not saying you should avoid these technologies, use them whenever you see fit, but what I'm saying is that, in my opinion, it's better to start with functionally simpler devices and or protocols. This way you are learning the basics, and you're also discovering the shortcomings of using basic, crude, primitive technology, let's say. And when you fully grasp this basic technology, then you can move on to more sophisticated devices or protocols, only when you feel the need to, when you need the extra functionality. Because they also come with an extra complexity, and even though this complexity is hidden from you, aka all these devices, Wi-Fi, Bluetooth, are easy to interface with using software libraries and high-level protocols, behind the scenes they are hiding a lot of complexity. And this channel is all about a journey in learning with a practical aspect, not just the practical aspect. Okay, moving on. So, let's say you want to communicate between two Arduinos via wire connections. You can do so pretty easily. Just connect them with wires and send your highs and lows according to your own communication protocol, or if you're using a software library, according to the protocol defined there. But more or less, that's all there is to it. Not much engineering. Now the question comes, could we do the same thing? Could we transfer the same signal over the air just as easily? Well, it seems not. Even if we could theoretically build such a circuit with some extra parts that could transmit what happens to be low frequency square wave over the air, it will be a bad and impractical design and will also cause a lot of interference with other designs. Why is that? Well, it has to do with how electromagnetic waves work and how they propagate, and it's a complicated topic which involves lots of physics and knowledge to properly understand it. But luckily, other people have already built these devices that do the job and do it right. In our case, the sender device encodes our digital signal on top of a carrier wave, which is a sort of a high frequency sine wave. Then, this travels over the air, or whatever happens to be between it and the receiver, and then the receiving device extracts the original signal from this wave and presents it as a digital signal, just as it was before we sent it. And now, using this, we're back in easy land. We've got ourselves what I would call a virtual wire. Sweet. Let's say we actually wanted to design these devices ourselves. What would we learn in doing so? Stop, let's not do it. I initially wanted to go all in on the details of how these devices work to satisfy my and perhaps your ever demanding curiosity, of course, like we do on this channel. But sadly, it's kind of a complicated topic to get it working right, and for me, at the current moment anyway, also in general, it's a complicated area of physics and electronics, so maybe one day, but not today. In the meantime, we can cover the simpler aspects of the transmission, such as how does modulation work? How do these devices take our signal and combine it with a carrier wave? Well, in general, there are several ways to do so, both for digital signals and for audio signals. So, let's start with audio signals, like your voice. Let's start even simpler than that, just a sine wave, like we see on the screen, a 1 kHz sine wave. We call this source wave, the one which we want to transmit. We call it the modulating wave. In order to optimally transmit it, we should encode it on a higher frequency, such as 400 MHz in this case, because a higher frequency has better propagation, not going into the details. One way we can do this, so how do we transpose our source information on the carrier wave, is to change the amplitude of the carrier wave in accordance with the amplitude of the modulating wave, like we see, just a moment, like we see here. So as you can see, if we follow the exterior contour of this modulated wave, we see it reflects the amplitude of the source wave at that particular frequency. So see, it's slowly changing, but at the same time it's on top of the fast changing carrier wave. What we see here is amplitude modulation. Another way to do modulation is to change the frequency just slightly. So the carrier wave frequency gets changed up or down slightly, again such that to reflect the amplitude of the modulating wave. How does this work in this case? Well, if we consider the minimum and the maximum values of the amplitude to be a minimum and a maximum frequency number, so for example, if the frequency is 400 MHz, the base carrier frequency, and then we call the minimum amplitude to be, let's say, 399 and the maximum to be 401, if we move between these frequencies at a proportional rate to the original amplitude, then we have just achieved frequency modulation. Now, let's go back to digital signals again. Here it is actually simpler, because while in audio we needed to modulate the whole variety of voltages corresponding to voice, to music, to whatever analog signal we were sending. In this case, we just have to send two values, one encoding the high voltage, the the 1, the logic 1, and 1 for 0, or the logic low. And here we have similar, we also have the carrier wave, and we have similar modulation techniques. They are called slightly different, but they represent almost the same thing. So ASK stands for amplitude shift keying, and it's the correspondent to amplitude modulation, but in this case we have only two values, so we have up, down, easier. Frequency shift keying, the equivalent of frequency modulation. Again, we use slightly different frequencies to encode the two values of 1 and 0. Then there's also phase shift keying. I will not go into the details, but the idea is that we encode the two values as phase changes. And there are also other modulation schemes, which we will not cover, because for the purpose of this video, all we wanted to know about is ASK, amplitude shift keying. This is what our transmitter and receiver devices use to communicate between each other. They use ASK, this type of modulation, and they work at this frequency, 433 MHz. As a side note here, if we add the antennas to either the sender or the receiver or both, it will increase their transmission range. If we keep them side by side while we do our tests, it will work anyway, but if you slightly want to increase your transmission, then you can add little antennas. Better to add it to the receiver than the transmitter, because it's a bad thing if you transmit too much energy and you interfere with other people's transmissions, and in some cases it's also illegal. So you should remember that. Moving on. Experimenting time. Actually, the experimenting time will be in a second video, because I realized the total length of the video would be 1 hour if I leave it like this, so I split it into a second part, which I'll be posting soon. Thanks for watching the first part, and hopefully I'll see you in the second one. See you!